Don't worry, folks, I'm not miming the whole video tonight, but I'll be a man of few words, as once again I'm having some technical difficulties. I'll just leave it at that. These are the volcanoes that are currently erupting. If you're wondering what's shaking, these are the parts of the earth that have been quaking. Hawaii, Hawaii, Hawaii. Only 1.5 magnitude quake in the past 24 hours. How about some more space? I think we've got more space. That is a 24-hour video from SDO. There's been some action, including an M-class flare. Another earthly directed coronal mass ejection is on the way. We expect that to arrive sometime on the 5th of February, February 5th. CME impact likely. Could cause some geomagnetic storm conditions depending on the magnetic field orientation and intensity. Those are 24-hour videos from Solar Dynamics Observatory. And here comes some more space weather stats. The radial flux now at 137, I think. 137. That's the 1 year Space Weather Enthusiast dashboard here. Forecasting a coronal hole high-speed stream, I think, on, what is it? Wednesday? So Wednesday into Thursday, we could see some activity here, including a CME impact on Thursday. Otherwise known as Thursday. So there's Noah's Enlil spiral. Earth's magnetic moment from space for the past 4 hours. Geomagnetically calm conditions. Earth's magnetic moment from the ground is next. By the way, we've got an exciting Ask a Particle Physicist segment tonight. That should be exciting. I'm excited. The question was submitted by this guy. Hopefully you'll like it. We'll get to it here momentarily. KP index 0.33. Very calm conditions from weak solar wind. So there's the ACE. The ACE there showing us 1 proton per cubic centimeter, only 333 kilometers a second for the speed. Discover here a lot faster and showing 2 separate regimes here. So solar wind varying between about 370 kilometers a second and 460 kilometers a second. Also the density varying and the plasma temperature. As you can see on that bottom frame is the plasma temperature. Current conditions are about 6 protons per cubic centimeter and 464 kilometers per second. There are the GOES magnetometers. Pretty smooth here for the past 3 days. And next, our top view ecliptic plane field plot. Yeah, that's a good one. So Earth is about to snap into a South Pole-oriented magnetic sector, folks. You can see it shown there in red. That's likely within the next 6 hours or so, I'd say. So South Pole magnetic sector coming soon. Here's a solar magnetic data, the B field, polar fields, and photosphere magnetism. There is our coronal hole line of sight plot, which brings us to coronal holes from SDO. We do have a well-defined one of North Pole orientation there in the Earth-facing strike zone. There's a great view of that from SDO. You may also see some plasma reverberations there, rippling across the surface of the sun, associated with that M-class solar flare. You can actually see some of the rippling there. Let's actually go back to this view for a minute. You can actually see transverse waves there coming out of that region where the M-class flare happened in your lower left screen. Just fantastic imagery there. And an active region just ahead of that coronal hole, which is not the most common feature to see. Next, we'll get to sunspots. And there you go. Sunspot number here just crossing the average again as it keeps getting higher and higher as we keep getting closer to solar maximum. So sunspot number here just crossing the 118 or something? 118 is the average right now. The smoothed average, current sunspot number here, right above there, about 119 for the current sunspot number. A little uptick since yesterday. So we do have a likelihood of large solar flares and proton events. And a bunch of new named sunspot groups. Here's our flare probability monitor and scoreboard. Let's take a look at the last 24 hours from SDO. And everything's looking mostly stable to me. What do you think? Let us know in the comments. By the way, all you viewers out there, help us narrate the rest of the video by leaving comments to narrate the video. That'd be great. Help us out by getting involved. Tell us what I should have said. Now, let's talk about solar energetic particle events. That's kind of important, right? Yeah, solar energetic particle events. Why? Because that's today's Ask a Particle Physicist segment, right? So there's the 7-day graph of the GOES proton flux. And what's interesting about this is that these relativistic particles showed up only 10 minutes after a large M-class flare. So what makes that interesting is that they were traveling at very high speeds. And I did some math here for you, just some rough math, nothing too precise, but so there's the past 7 days of GOES proton flux. Again, the peak flux of this, or the relativistic particles, started to show up here only 10 minutes after the peak flux of the solar flare. So at 93 million miles, traveling for 0.16 hours or 10 minutes, that means that those particles reached 259,842 kilometers per second approximately, or if you prefer, 259 million meters per second. So, but just to tie that into the solar wind right now is only, 460 kilometers a second or something like that. These particles are traveling at 259,000 kilometers per second, just to put that in perspective to how fast those particles are moving with respect to the regular solar wind. So next, just to talk about the Ask a Particle Physicist segment, if you want to get involved yourself, do it over at smashomash.com/forum. There's a forum for general science, and that would be a place to ask a particle physicist. The particle physicist is Mr. Bagashov. We'll talk more about that in a minute. Let's kick off the segment while solar energetic particles are fresh in our minds. Now, we also have a playlist for Ask a Particle Physicist, just so you know. So you can check that out at youtube.com/smashomash/playlists. And there's a list of all of our playlists there. And every Friday we release the last week's video. So right now it's only available on last week's Friday edition of the Daily Space Weather Show. But then each week, and paying Smash Team members get that early and so on. But I'm not going to get all in depth into that. Let's just kick off the Ask a Particle Physicist segment. Take it away, Eugene, the monotone from Minsk, coming at you.
The question is, we recently had the strongest solar energetic particle event of solar cycle 25. What happens during an SEP, including what the GOES and 16 and 18 proton flux are measuring? Well, so first of all, what is a solar energetic particle event? It's the emission of high energy protons by the sun. And it usually happens, like we catch them, these energetic protons on Earth, when the sun, like there's some sort of flare or CME that happens, like somewhere here in the right portion of the sun as viewed from Earth, because that's the area, roughly the area where we connect to the sun by the interplanetary magnetic field lines, as we've seen in previous videos. Okay, so then these energetic protons created by the flare or whatever other event on the sun might follow these magnetic field lines and reach Earth very quickly, because they have a lot of energy. So it takes maybe 10 minutes, half an hour, up to an hour. So the regular, slow plasma, it may take it like 2 or 3 days to reach Earth, and these faster particles reach Earth in a matter of like tens of minutes or hours at best. Okay, so what do they do? Well, you may remember we previously discussed like what happens to regular protons from the solar wind. So they get deviated by the magnetosphere, right? We've discussed the exact, more or less exact mechanisms how that happens. But these protons are much more energetic. They're moving with almost this, like the significant fraction of the speed of light. Could be like a half of the speed of light or something. So they aren't as easily deviated by the magnetic field. So they can move closer to Earth. Like eventually they would be picked up by like these polar magnetic field lines, and most of them do get into the polar areas because of this. Some of them do get into the lower latitudes for sure, but most of them still get into the polar areas. So what do they do? Well, first of all, like for satellites in orbit, they can cause like charge buildup. They ionize the stuff that the satellite is made of. They ionize the biological tissue, so it's not very cool, for the astronauts to get into this radiation storm. What can they also do? They will ionize the atmosphere, of course, which causes, for example, an increased absorption of high frequency radio waves. So it can cause potential issues with like GPS signal reception and things like that. So basically the ionosphere becomes less transparent and even less reflective for radio waves. Like it starts absorbing them. So it's not very cool for technological things in this respect. That will be it. I mean, I've seen some papers that have discussed like hypothetical impacts of solar energetic protons on some other stuff. Like some paper a while ago was talking about how like they found a correlation between forest fires and solar energetic particle events. So maybe these high energy protons actually may trigger some sort of, I don't know, a spark, roughly speaking, or something to that effect. I mean, they do create large atmospheric like showers of charged particles, including ions and electrons. But this mostly is concerning like the high altitude, like ionosphere, stratosphere stuff. But apparently, like, who knows? Maybe some of these particles do reach Earth, actually. Like, I don't really know. I mean, their energy is lower than the regular cosmic rays. So, I mean, the cosmic rays, which are the galactic cosmic rays. I mean, the galactic cosmic rays their typical energies could be a giga electron volt. Whereas these protons from the sun, they're typically in like 10 or 100 mega electron volts. So that would be a 10 or 100 times smaller energy than the galactic cosmic rays. But still, who knows? Because of their higher flux, maybe they might cause some other effects. By the way, in high altitude, when we're talking about like airplanes, especially like the planes that fly near the polar areas, they also receive a higher radiation dose during these events, and other things like that happen. But on the level of like sea level, at the bottom of the atmosphere, like not much changes, to be honest. So it's mostly like polar regions and high altitudes that are affected. Okay, and what was else? What was the other part? So what are GOES measuring? So it's this graph, I assume, that we're talking about. So GOES is a geostationary, I'm not sure what O means, like Earth observing satellite, let's just call it this. So geostationary means it's at an altitude of about 36,000 kilometers, so it's pretty far away from Earth. So it's kind of outside the Earth's magnetosphere, so it receives, well, more or less, there's obviously some elevated magnetic field there still, but with respect to the solar wind, I mean, but still mostly outside the Earth's magnetosphere. So, and they measure literally the flux of these protons. You see the particles per centimeter squared per second per steradian. So steradian is a solid angle. So 4 pi steradians, which is roughly 12.5, would be like the whole sky. So if 1/12 of the sky would be one steradian roughly. So yeah, in the typical flux, right now it's slightly elevated from this last storm, but still, as you can see, the typical flux around 10 mega electron volt range is about one particle per centimeter per second. Centimeter squared, I mean. And as you can see, their threshold for the storm is 10 particles, right? So 10 times higher than usual. And yeah, that's what we're measuring. So yeah, as you can see, it's not a whole lot of particles. I mean, 1 particle per centimeter per second. I mean, in a centimeter of water, like a cubic centimeter of water, there's like 10 to the 23rd power of particles. But still, since these protons have a lot of energy, you see 10 mega electron volts, and again, like the ionization energy of a hydrogen atom, let's say, is 13 electron volts, right? So one such proton, like theoretically, might ionize how many? I don't know, like 100,000 atoms, something like that, and that's a lot. That's a big charge already, right? If we're talking about 1 centimeter cube. But obviously, as I've said, this is the flux at the geostationary orbit, so it would be much lower when they come to Earth, because the magnetosphere would still like deviate them significantly. And once again, as I've said, in lower latitudes, the flux would be minuscule. Like most of this stuff gets into the polar regions, after all. But yeah, still, I mean, maybe it can cause something else. Yeah, like as usual, we're only starting to study all of this stuff. Like humanity has only learned about this very recently, like what, 50 years or something. So yeah, much more research would be needed of how this might impact, well, whatever really, like whatever processes that happen on the Earth and in our nearest space environment. Well, hopefully this answers the question.
Hey there, thanks Eugene. So that's our Ask a Particle Physicist segment for today, and again, we got a playlist for that. We do put those videos out a week early for Smash Team, paid Smash Team members. Smashomash.com/Smash Team if you want to support the channel. But yeah, Eugene, make sure you go subscribe to his channel, Eugene the Philosopher. We should have a link up there for you mobile viewers. And yeah, thanks again, Eugene. And by the way, the track that started out this video is called Settle It. We do have a Spotify account, Golden Cat Productions. Check us out over there if you haven't already done so. Golden Cat Productions. We're on YouTube Music as well. Also iTunes, Amazon Music. So lots of places to download the Golden Cat Productions tracks, the original music. And so solar flaring, there has been an M-class event. One M-class event. Let's take a look. There's 94 angstroms. It was down there in the southeastern quadrant, which, statistically speaking, probably remains, I would say, remains the most likely place for a large solar flare. There are more sunspots appearing to be about to rise there in the southeast also. Now, I don't look at far side imagery, so I don't really worry about all of that. I try to forecast using magnetic fields, and it's been quite promising, actually. Anyway, here's an extreme close-up of the T-mass, the most active sunspot for February 2nd. 2-2. I guess it must be official ballet day, as it is 2-2, right? And moving right along here, we'll show a star chart. I think we'll show a star chart next. There we go. And the sun having just set here over Lehigh Valley, Pennsylvania. Solar system forecast. New moon coming. Astronomy photo of the day. And next we'll cover CMEs. So there is one more CME headed toward Earth. It's not going to be a major geomagnetic storm, but we could see some geomagnetic storm conditions, KP 5 or 6, from this one. You can see it on that imagery there. We'll rock this back for a moment. Let's switch to the zoomed in view. There we go. It's not that one. It's not that one. It's that one, I think. Oh, wait. Hasn't happened yet. Hold on. I think it's that latest one. Hold on a minute. Yeah, that's the one from like 1200 Universal Time today. Looks like a minor CME impact is coming. So there is the synced up imagery, and you'll see one of the, oh, check it out, another comet, folks, right down here, another sun diving. Look at that, nice. That one has got quite a bright coma. So how about them apples? Not too bad. And yes, that the earthly directed CME did come from this series of filamentary outbursts. So, yep, that's what's going on. And let's continue on here before I lose all semblance of being able to function. Next is solar filaments. And there are some. A lot of instability continues in the southeastern limb. That's by far the most likely place for a large solar flare, both from behind the limb and on the existing sunspots. So we'll be keeping an eye on it. And when I say eye on, well, pardon the pun. So here we go. There's the full disk as we transition into bonus features. Bonus features, folks. And on to meteorology. Starting out with total cloud water today. Because reasons. I have my reasons. Try to figure them out yourself. Total cloud water. Total cloud water and surface winds. All right, quick consumer tip about this map. So, the resolution on this is 1 kilometer, which means 1 pixel on this map is a kilometer. If you think that this is a chemtrail, or this, Please realize that individual plane contrails are not visible on a map with a 1 kilometer pixel resolution. That means one dot, if you zoom all the way in, one dot is 1 kilometer. I think it's actually 2 kilometers, but even if it's 1 kilometer, 2 kilometer resolution, folks. 2 kilometer resolution. So, have you ever seen a plane leave a 2 kilometer wide contrail? I know I certainly haven't. So, yeah, there's that. It's not weather mods, it's pressure gradients. So here's the satellite map for the U.S. as darkness falls. Weather.gov map is next. Lots of warnings for Hawaii. Weather.gov is where to get that map. Next, Tropical Tidbits forecasts. I'm going to show you one pressure and precipitation. So there you go. There's your weather map for the day. Lower 48. Here is your lightning map for the past 10 hours. Strong low over the Central Atlantic, which we almost showed a close-up of, but not quite. Real-time lightning map is next. Quite a bit of terrestrial strikes in the U.S. Texas, Oklahoma, and a little bit in Kansas. There's an active cell for you near Colorado City. We'll close this mother out with Doppler radar for the lower 48. Clouds and fog. And of course the water vapor map. And your lower 48 recap. And thanks for tuning in to the Daily Space Weather. I've been your host, Dan, a.k.a. Smash-O-Mash, signing off. And may that solar wind be at your back.